Thank my brother for introducing me. Also, please, if you can't hear me, shout, because it's not worth it if you can't hear. And I've been warned that sometimes people don't hold the microphone correctly, so do let me know. All right, so this is, well, unfortunately, the title that's written here gives away part of the point of the talk, but it's okay. So I'm talking about graphs, about coloring graphs with forbidden induced subgraphs. And this is joint work with two of my PhD students, Peter Machel and Ming-Shan Zhou, and also Juraj Stacho, who was a postdoc at Columbia until about 2 weeks ago. All right, so it's about coloring graphs. Probably I don't need to remind you, but I'll remind you anyway. Coloring graphs means assigning colors to its vertices in such a way that if two vertices are adjacent, then they get different colors. And coloring is hard. If I give you a general graph and ask you to color it with a fixed number of colors, or to see, to check whether you can color it with a fixed number of colors, that's NP-complete, except if I only have 2 colors. But for any number of colors larger than 2, checking if a graph is colorable with that number of colors is NP-complete. So in particular, it's even NP-complete to check that it's NP-complete to check if a graph is 3-color. Now, this next theorem is not really related to anything I'm going to say, but I feel like it's a good way to illustrate how hard coloring is. If I give you a graph and I tell you it's 3-colorable, and I ask you to color it with some not very large number of colors, then the best you can do is this name, is n to the power 4 over 11, where n is the number of vertices. And that's the result of Torop and Kawarabayashi. All right, so probably you knew, and if not, maybe I've convinced you that coloring with more than 2 colors is a difficult problem. And so then one asks, how can I make the problem simpler? What conditions can I impose on the graph so that the coloring problem becomes polynomial? Well, there are all sorts of things you can do, but I have done a lot of work on induced subgraphs, so I'm interested in imposing conditions that have to do with forbidding induced subgraphs. So just to remind you, a little graph is an induced subgraph of a big graph if you can get the little graph from the big graph by deleting vertices. So you delete some vertices. Now, if you delete the vertex, you have to delete all the edges incident with it. But that's all you can do. You're not allowed to take 2 vertices that were adjacent and just delete the edge between them. That's not a legal operation for taking induced subgraphs. All right, so now the question is, what if I don't just give you a general graph, but I give you a graph with some induced subgraph excluded? Does that make the coloring problem simpler? And the answer is usually no, but let me go through this more slowly. So first of all, there's a theorem of Kaminsky and Lozhin that says that for any k, at least 3, k coloring graphs of large girth is NP-complete. The girth is the length of the shortest cycle in a graph. And what they proved is that if I give you, if I look at graphs of girth at least 100 and try to k color them, that's NP-complete. And if I look at graphs of girth at least 1,000,000 and try to k color them, that's NP-complete. Right? For every girth, k coloring graphs of this girth is NP-complete. Now, what that tells you is that if I exclude, so if now remember I'm thinking about trying to k-color graphs with certain induced subgraphs forbidden. So now suppose I'm trying to forbid an induced subgraph that has a cycle. I claim that does not help with complexity of k-coloring because of their theorem, right? Say here's a little graph on 10 vertices I'm excluding. Well, let's look at all graphs of girth at least 11. Slow down. So if I'm excluding a little graph that has a cycle, here's a graph on 10 vertices I'm excluding, and it has a cycle. Now let's look at all graphs on girth at least 11. Well, they will not contain my little graph H because my little graph H has a cycle, which has at most 10 vertices. But on the other hand, Kaminsky and Lozhin tell me that k-coloring graphs of girth at least 11 is NP-complete. So excluding anything with a cycle doesn't help. All right. So next, here's another big class of graphs excluding which doesn't help. And let me get there slowly. So edge coloring is NP-complete. That's a theorem of Hollier, right? If I try to edge color a graph with at least 3 colors, that's NP-complete. Now that means that vertex coloring line graphs is NP-complete. Now what did I just say? Well, a line graph, if I start with a graph, its line graph is simply a new graph that records intersections between edges. More formally, if I start with one graph to build its line, so if I start with a graph, its line graph would have as its vertex set the edge set of the graph I started with, and 2 vertices in the line graph are adjacent if the corresponding 2 edges share an end. All right? So edge coloring a graph is the same as vertex coloring its line graph. Now, by Hollier's theorem, vertex coloring line graphs is NP-complete. Now, the next observation is that line graphs don't contain this graph, called a claw. And that's not difficult to see. If you think about it for 5 minutes, you'll convince yourself that line graphs don't contain claws. So now that means that if I'm trying to exclude a little graph that has a claw, that's not helpful for complexity of k-coloring, because in particular I still get the class of line graphs, not to contain this graph. And k-coloring there is NP-complete. Okay, so excluding anything with a cycle is not helpful. Excluding anything with a claw is not helpful. So what's left? Well, that's what's left. Excluding graphs that don't have cycles, so they're forests, and don't have claws, so they're disjoint unions of paths. Every component is a path. Right, so here's the only question that remains open as far as k-coloring graphs with a certain fixed induced subgraph forbidden goes. I fix a graph H, which is the union of disjoint paths. I look at H-free graphs. I want to color with at least 3 colors, and I want to know what the complexity of that is. And what I'm going to do for the rest of this talk is focus on the case when H is a path. Just to fix notation, so P sub t is a t vertex path. So, there's a little bit of confusion. P sub t is sometimes the t vertex path and sometimes the th path. And it doesn't matter, but it's good to fix notation. So we're going to commit ourselves that pt is a t vertex path. Okay, so then there is a table, right, in which you can summarize everything you know about this question. So you're trying to k-color and you're excluding pt. And some things are polynomial, and some things are NP-complete, and some things are unknown. And let me talk about that a little bit. So first of all, I should say all the results in this table are from these 2 papers. So the results in fuchsia are more recent, and they're from the paper by Huang, and the results in black and red are older, and they're from this paper. All right, so what does this table say? Well, first of all, if I exclude a path on at most 5 vertices, then everything is polynomial. If I exclude a path on 6 vertices, then 3 coloring is polynomial. If I want to color with at least 5 colors, that's NP-complete. And there's one open case, and that's 4 coloring. We don't know the complexity of 4 coloring P6 reflex. Now, as you can see here, everything else in this table, when I color with at least 4 colors, is NP-complete, right? If I exclude any path longer than 6 vertices and I want to color with at least 4 colors, that's NP-complete. So the other open cases, open situations, are 3 coloring. If I exclude anything longer than 6 and I want to 3 color, then we don't know the complexity. So one thing about this table, right? Obviously this does not contain, the way it's stated, it does contain all the results for all natural numbers. But in fact, you can quite easily convince yourself that if I have a point in this table that's NP-complete, then making the path longer or increasing the number of colors still gives you an NP-complete instance. And on the other hand, if I have a point that's polynomial, then making a path shorter or decreasing the number of colors remains polynomial. So if you know a point, you can. Right. All right. So what I'm going to do is talk mostly about the case of 3-coloring graphs with no 7-vertex path. And then I'm going to say something about 3-coloring graphs with no 8-vertex path. And then there's a sporadic open case for 4-coloring, so I'll say something about that also. All right, so but this is what's known at the moment. All right, so our theorems. So the first theorem is that, I can go back to this table. The first theorem is that actually this question mark, the t equals 7, k equals 3 question mark, is no longer a question mark. So there's a polynomial time algorithm to 3-color graphs with no vertex of, 3-color graphs with no path of length 7, with no paths on 7 vertices. And I should say who proved which theorem. So this first result is with Peter Machelli and Ming-Hsian Zhou. That does not involve Uri. So then our second theorem is about the 4-coloring problem. So we can't quite solve it, but we can prove that if in addition to excluding a 6-vertex path, you also exclude a 5-cycle, then the 4-coloring problem becomes polynomial. And excluding a 5-cycle is in some sense a halfway point. I'll explain later why, but it's a somewhat natural case to look at. And then this is a theorem of all 4 of us. And then the last result, and that's just Uri, Stachel, and myself. That's about 3-coloring pH-free graphs. So it was known before we started that if you try to 3-color pH-free graphs with no cycles of length at most 6, then it's polynomial. And so we were looking at excluding shorter cycles. So you can see it says here. So if you're pH-free and you also exclude triangles and fourgons, then all such graphs are 3-colorable. If you exclude P8 and triangles and 5-gons, all such graphs are 3-colorable. If you exclude P8 and 4-gons and 5-gons, but you're allowing triangles, well, that gets a little bit more interesting. Not all such graphs are 3-colorable, but they're only boundedly many abstractions, namely 5. So, for algorithmic purposes, this is still good. You can test in polynomial time whether your graph contains one of those guys. One thing I should say, these 5 abstractions, they're abstractions as subgraphs, not as induced subgraphs. But you can work a little bit harder and get a bounded number of induced subgraph abstractions. All right, so now I'm going to talk about each theorem in some detail. I guess, no, not quite. So, all right, so as I said, right, there are a lot of open cases for 3-coloring, and there's only one open case for 4-coloring, so let's focus on 3-coloring for a little while. So Paul Seymour made a conjecture that if I exclude a fixed length path, then there is boundedly many abstractions to 3-coloring, right? Or equivalently, if I exclude a fixed length path, then any abstraction, any minimal abstraction to 3-coloring has boundedly many vertices. Now, obviously, if this were true, then you would get a polynomial time algorithm for testing 3-coloring with a fixed length path excluded, right? You just go and check if any of the abstractions is present. So I used to not believe this conjecture at all, and then I started working on it, and maybe I believe it a little bit more now. But anyway, I'm going to show you some things that support this conjecture, and then some places where I think you'll find a counterexample, and I think I don't have an opinion on whether it's true or false at the moment. So now let me talk about proofs of the theorems. So, all right, we started by talking about coloring. Now I'll need a variant of coloring called least coloring. And what least coloring is good for is a situation where you've pre-colored part of your graph, and now you want to see if this pre-coloring extends. So let me tell you what least coloring means. Well, you have a graph, and for every vertex, you have a list of allowed colors. And now you want to check, and you color your graph where every vertex it's colored from its list. So you still have the rule that adjacent vertices have to get different colors, but you now have the additional rule that not every color is allowed at every vertex, right? Every vertex has to use a color from its list. So coloring is in particular list coloring. You just give, K coloring is in particular list coloring if you just give every vertex the list 1, 2, 3 through K. All right, and I'm going to say that a pair G and a list is colorable if there is a coloring so that every vertex is colored from its list. Now, well, like I said, this is good for when you've pre-colored part of your graph, because what does it mean, pre-coloring part of the graph and then trying to extend it? Well, that means that for some vertices, some colors are now forbidden. Well, you can record it by removing some colors from their list, right? All right, and so now the idea of all of our proofs is to reduce the 3-coloring or the 4-coloring problem that we started with to polynomially many list coloring problems. Now, so far, so what does it mean to reduce? That means that the original graph is colorable if and only if at least one of the list coloring instances is colorable. Now, okay, so far I haven't gained anything. List coloring is harder than coloring, and now I have many problems instead of one. Well, the thing is, I'm going to make these list coloring problems simpler than my original problem, and I'll explain what I mean by simpler. Okay, so but this is the idea. For those of you who maybe know about Conforti and Rao's idea of cleaning, that's very similar. Basically, what they do is they start with trying to, that you want to find something in your graph, and then you prove, for example, that there's an edge you can delete, and you still haven't ruined the thing you're trying to find. Well, now what you do is you go one by one and try and delete edges. So now you have n squared instances, and in one of them you still have the thing you were looking for. Maybe if you didn't know what cleaning was, this wasn't very helpful, but it's a similar idea. All right, so let's keep going. So the next two slides explain which list coloring problems are easy. Okay? I said I'm going to reduce one coloring problem to many list coloring problems, which are easier, so that's what it means. One list coloring problem that's easy is if every vertex has list of size at most 2. Well, that you can record as just a 2-set problem. And so then, of course, you can solve it in polynomial time. That's the theorem of Edwards, but it's actually not a hard theorem. So that's one tool we use. If I manage to reduce all the lists to size 2, then I'm happy. Another tool is an extension of Edwards' theorem. And what that does, so you still have the rule that every vertex has a list of size at most 2, but in addition, you're allowed to have polynomially many subsets of vertices, each of which is constrained to be monochromatic, right? So I have the set S1, and everybody in S1 has to get the same color. I'm not telling you which color, but they all have to be the same color. I have the set S2, everybody in S2 has to have the same color. And that's, again, not very hard to reduce to 2-set. It was, I believe, first used in this paper, which I had mentioned before, but they don't prove it, they just quote it. I heard this theorem first from Juraj Stachel, but he refuses to admit that it's his theorem, so I don't know whose theorem it is. But, I learned about it from Juraj. All right, so this is another tool we're going to use, and then there's a couple more, but I'll mention them as we go. So now let me finally get to some of the theorems. So the first theorem is that if I exclude a 7-vertex path, then testing if a graph is 3-colorable is polynomial. So let me talk about that. Well, here's sort of what you would like to do. You would like to prove that every P7 graph has a dominating set of size at most 100. This is completely false. So if you see me, this is false. Don't be worried. This is not my last slide, but it's something that would be nice if it were true. So a dominating set means a set of vertices so that everybody else in the graph has a neighbor in that set. So suppose I could prove that every P7 graph has a dominating set of size at most 100. Well, now take this set, pre-color it. Now everybody else has a neighbor in it. So for everybody else, their list goes down by at least 1. So for everybody else, their list now have size 2. And that I can test, that I can check by Edwards' theorem. So all I need to do is try all possible colorings of my dominating set of size 100. There's only 3 to 100 of them. So I've reduced my one hard problem to 3 to the 100 easy problems, easy list coloring problems. All right, so as I said, this is not true. There are many examples where you don't have even a logarithmic size dominating set. But in all these examples, you have something else that helps you color. Like you have a vertex of degree 2, or you have one vertex that dominates another. So there's some question there. When does there exist a bounded size, or even a logarithmic size dominating set? That would still be helpful. And maybe you can prove some theorem that says either there's a dominating set, or there's something else that's algorithmically useful to you. I don't know such a theorem, but I don't know a counterexample to it either. All right, so this is what we would like to happen. In reality, this doesn't happen, but what we do is kind of massage our graph until something like that does occur. So let me explain this. So first of all, I'm going to say that a graph is reducible if, in order to test whether this graph is three-colorable, it's enough to test whether a smaller graph is three-colorable. And so the first half of the slide is a rigorous definition of that. So you don't need to read. Reducible just means in order to color this graph, it's enough to color a smaller graph. So here's one example of a graph being reducible. If I have what's called a dominating or a dominated vertex. So I have these two vertices, u and v, and they have the property that every neighbor of u is also adjacent to v. So maybe I should explain what this kind of schematic picture means. So this is v, these are the neighbors of v, these are the non-neighbors of v, then this is u, and these are the neighbors of v, all right? And so every neighbor of u is also a neighbor of v, and u and v are non-adjacent. Well, why is this a good thing? Delete u, color what's left, and now give u the same color as v. So that's an example of a reducible graph. I could delete u and just color the graph without u. And we'll have a few more reductions, but we can always assume that my graph is not reducible. Right? If there's some reduction, then I don't need to worry about this. All right, so there are two halves to the algorithm. In the first half, we assume that the input is triangle-free. And then there are various structural things you can prove, right? If you don't have a long path and you don't have a triangle, somehow you know more about your graph. The second half of the algorithm is when we assume that the graph contains a triangle. Well, then structurally you're in worse shape because all you did was exclude a long path. But on the other hand, you know more about coloring, right? If I have a triangle, there's only one way to three-color it. And then if I have a vertex with two neighbors in a triangle, well, the color of this vertex is forced. And so a bigger chunk of coloring is forced. So, and this is kind of how the algorithm works. In the first half, we rely more on structure. In the second half, we rely more on the fact that some of the coloring is forced. Let me do some more details of that. So let's think about the triangle-free case first. If my graph is bipartite, that's something I can test and output the two coloring. So I can assume there is an odd cycle, and because there are no long paths, the length of the odd cycle is bounded. Namely, all I can have is a cycle length 5 or a cycle length 7. And now I'm going to, so here's a picture of a cycle length 7. And now I'm going to partition the rest of the graph by, partition the rest of the vertices by their distance from the cycle length 7. So set X are vertices with a neighbor in the cycle, set Y are vertices that don't have neighbors in the cycle but have neighbors in X, the set Z are vertices that they're distance one further, don't have neighbors in the cycle, don't have neighbors in X, but do have neighbors in Y. And now I claim that's it, you can't go any further. So let me explain that. Well, so let me explain. Well, let's look at the vertex in X and let's think about its neighbors in the cycle. Because my graph is triangle-free, it cannot have two consecutive neighbors. But because the cycle is odd, I can't go yes, no, yes, no, yes, no, yes, no. Right? Somewhere I have to go yes, no, no. And then, so now if you choose any vertex here and you trace it back to the cycle, so it goes Z, Y, X, neighbor of X, non-neighbor of X, non-neighbor of X, you'll see this is already a path of length 6. So you couldn't go any further. All right, then you can continue this kind of analysis and you can prove that actually set Z is stable or independent, meaning there are no edges there, and actually every vertex in Z is dominated by some vertex in X. But remember we said having a dominating vertex or a dominated vertex is good for us. It's a reducible configuration, so I can assume the set that doesn't exist. All right? So now, so now the idea would be you try to pre-color the seventh one, which means you go through all possible 3 colorings of the seventh one. That immediately reduces the lists of people in X to size at most 2. And the only vertices that we still need to deal with are vertices in Y. And so what we do now is basically try and guess a dominating set. It's not exactly true what I'm saying, but it's kind of true. You guess, let's say, 10 tuples of vertices. So you go through all possible 10 tuples of vertices. And you know that at least one of them would give you a dominating set together with the C7. And now, so now you try and pre-color each of these possible dominating sets, and that gives you polynomial many instances of least coloring problems, but the least coloring problems are easy. And then you prove a theorem that that's in fact true, that you could guess such a set. Again, not quite true, but close enough for this level of detail. All right, so this is the triangle case. Now let me talk about the case when you use a triangle. Well, first of all, if there's there's more than a triangle, if there's a clique of size 4, then I can stop right away because I'm trying to 3-color. Okay, so now let me tell you about one more reducible configuration, just because we like it. Okay, so suppose I found a vertex whose neighborhood is connected. I claim that's good for me. I claim then the graph is reducible. Because why? Well, so here's this vertex V, here's its neighborhood. Now what does it mean? So I'm trying to 3-color. If the neighborhood is connected, that means the neighborhood is 2-colorable and the 2-coloring is unique, right? I mean, first of all, I can go through all the vertices and check other neighborhoods 2-colorable. If somebody has a neighborhood that's not 2-colorable, I can stop. And that's something I can easily do in polynomial time. So now if I found a vertex whose neighborhood is connected and 2-colorable, that means it has a unique 2-color. And that's a good thing, because what you do is you basically, right, so you can calculate this bipartition of the neighborhood, and now you basically contract the 2 color classes, meaning you replace the first color class by a single vertex, and you make this new vertex adjacent to everybody in the graph who used to have a neighbor in this set, and the same for the other color class. Well, now, this graph is colorable if and only if this graph is colorable. In one direction, it's clear. So if this is colorable, then that is colorable. That's easy. In the opposite direction, that's where I use the uniqueness of the 2 coloring of the neighborhood of V. Right? Everybody here, everybody in this big set A, has to get the same color. That's the only way I can 2-color the neighborhood of V. So it's enough to find a color that works for this vertex A. A harder question is, when I do this contraction, does the graph remain P7 free? And the answer is yes, but that's a fairly hard technical proof. But you can do it. All right, so I go from here to there. Well, usually I made my graph smaller. There's a small possibility that I didn't, right? If this was size 1 and this was size 1. But then I have a vertex of degree 2, so I can definitely delete it. And the graph becomes smaller. The colorability doesn't change. All right, so the upshot is if I find a vertex with connected neighborhood, that's good for me. That's a reduction. Okay, so now let's use all this knowledge. So like I said, in the case when there's a triangle, I'm going to try and force as much of the coloring as possible. Well, I start with a triangle, and now I build what's called a tripod. And what that means is I add vertices whose color is forced. So I start with a triangle x1, x2, x3. Now I have a vertex called x4 that's adjacent to x2 and to x3. Well, I'm going to put it in the same blob as x1 because its color is forced to be the same as the color of x1. Then, so I have a vertex x5, has a neighbor in the first blob and the last blob, so I put it in the second blob because its color is forced to be as the color of the vertex in the second blob. And you can keep going, right? You can keep going, you can make it maximum. And you get a chunk where the coloring is forced. Now, just one thing, remember Seymour's conjecture about bounded size abstractions to 3-coloring. I mean, this is, to me, the first candidate for giving a counterexample, because suppose I built this thing, what we call a tripod, and now I add another vertex with a neighbor in all three sets. So clearly this is not three-colorable. And I cannot prove that there's always a way to make it bounded size. It seems to me you can build a rich enough tripod that, this thing would be unbounded. All right, anyway, so but back to the proof. So we start with a triangle, we build a maximal tripod, we check that each of the blobs is stable, because if not, then I can immediately tell my graph is not three-colorable. And now everybody else in the graph has neighbors in at most one blob, right? That's what the rest of the graph looks like. Because if somebody, so here ABC is the tripod, if somebody had neighbors in, let's say, both A and B, well, I could add it to C. So that contradicts maximality. All right, so I have my tripod. I have vertices with neighbors in exactly one set. And then I partition everybody by their distance from the tripod, just like we did for C7. And now, same deal. I'm going to pre-color the tripod. Now, obviously, C7 has boundedly many three colorings. Well, but so does a tripod, because everything is forced. It's an unbounded size graph, but it only has boundedly many three colorings. So that's equally good for me. Okay, that's one. All right, so I pre-color the tripod. Now, people with neighbors in it, their lists go down to 2, so they're good for us. As before, as in the C7 case, the last set you could sort of naively get is actually empty. Similar arguments give you that all the vertices there are either dominated or have connected neighborhoods. And obviously I'm not going to do the argument. So then there's a small part of the graph that you need to deal with, and you do, and I'm not going to do the details. All right, so that did the first theorem. That did the theorem of three-coloring P7 figures. Now let me move on to talking about four-coloring graphs with no six-vertex path and no five-cycle. Now I promised to say why excluding a five-cycle is somewhat natural. Well, so you know what perfect graphs are. A graph is perfect if and only if the clique number and the chromatic number are the same for all induced subgraphs. And there's also an induced subgraph characterization of perfect graphs. So a graph is perfect if and only if it doesn't have any induced odd cycles of length at least 5, and the same in the complement. Now, so if I'm trying to four-color and my graph is perfect, then it's very easy to check if it's four-colorable. You just check, is there a clique of size at least 5? So I can assume my graph is not perfect. But now, so I can assume my graph is not perfect. I can assume there is no clique of size at least 5. And then, so there should be an abstraction. And in this situation where there's no C5 and there's no P6, the only abstractions you can have, back up. So there is an abstraction. In the P6 case, there are only two possible abstractions. One is P5 and one is C7 complement. So when I also forbid P5, when I also forbid C5, now I definitely know that I have C7 complement as the abstraction, right? So from having two possible abstractions, I reduced. I didn't reduce, but I'm looking at a special case when one of the abstractions is definitely present. All right. So just to be completely clear, we did not reduce it to this case. We just looked at this case, but that's an initial case here. Okay, so as I said, I can assume there is a C7 complement. And now you partition everybody by their distance from the C7 complement, as we always do. And that's as far as you can go. You can check, it's not hard. So now let's focus on X. And it turns out there are two kinds of vertices in X. There are vertices whose neighborhood within the C7 complement contains a triangle, and then there are vertices whose neighborhood in the C7 complement doesn't have a triangle, but then they start a four-vertex path. So for that kind of vertices, there's a four-vertex path going, my vertex in X, and then three other vertices in the C7 complement. And it turns out both of the things are good for you. So I'll explain why. Right, so the strategy would be, again, you pre-color the C7 complement, and then, well, if somebody had a triangle in its neighborhood, if somebody in X had a triangle in its neighborhood, now its list goes down to 1. So then I can, propagate the good news. Its neighbors, their list would go down to 2, and that's a good thing. If somebody wasn't adjacent to a triangle, well, its list is still big, but at least it cannot be mixed on a faraway edge, right? If somebody here starts a 4-vertex path going in this direction, it cannot also start a 3-vertex path going in that direction. That will give you a P6. So that means somebody here who is small, who is of the second kind, cannot be mixed on a component of that stuff. Now there's an obvious lie written here. I said that if a vertex is small, then it has size 2. Well, that's not true for vertices with exactly one neighbor in the C7 complement. But we're going to sweep them under the rug because really they work like vertices with no neighbors at all in the C7 complement. But that's technical. Let me not go into that. Okay, so now what we do is, so I have the C7 complement, I have the vertices in X, and now I look at components of everybody else. And now I look at how these components of everybody else attach. So suppose I have some component that only attaches to big vertices, only attaches to vertices whose color is fixed after I've pre-colored the C7 complement. Well, that's good for you because that works like a clique cut set. You know, read all these arguments. If you have a graph and you can delete a clique from it and the graph becomes disconnected, then to color this graph, it's enough to color the first half and the second half, and then you can match the two colorings on the clique. Well, it's the same thing here. I don't have a clique that disconnects the graph, but I have vertices that are partitioned into 4 sets, and each set has a fixed color. So it works in the same way. So if somebody only attaches to big vertices, that's a good thing. So there's a component that attaches to small vertices, and then, well, so it's not as easy anymore, but at least I get somebody who is complete to that component. And that's again good for coloring. I'm not going to do the details, but that's again good for coloring. All right, so that's that theorem. And now I'm going to say even less about the last theorem. So the last theorem is, just to remind you, I'm thinking about 3 coloring graphs with no 8-vertex path, and I'm forbidding all sorts of short cycles. Right? So I'm forbidding C3 and C4, or C3 and C5, or C4 and C5. So what happens there? It's sort of pretty. I mean, I think the kind of nicest thing about this theorem is its proof. So a lot of the time what happens is you can just grow a structure. Say you assume your graph has no C3 and no C4, but it contains a Peterson graph. Well, then basically the whole graph is the Peterson graph plus floors. I'm lying a little bit. There might be like vertices of low degree or something like that. But those we don't care about. We're just interested in coloring. So somehow, if you exclude things that are obviously good for coloring, these graphs behave very nicely. The only case where these kind of tricks don't work is when you exclude a 4-cycle and a 5-cycle and you allow triangles. But then there's another trick that works. So remember vertices with connected neighborhoods that were good for 3 coloring because you could reduce something because there were 2 sets whose coloring was forced. Well, so here I'm not just trying to get an algorithm, I'm actually trying to describe all obstructions to 3 coloring these graphs. So saying, I can contract is not good enough, but it turns out you can do a similar argument and it would work for describing obstructions. What I mean is, so what I call a connected star cut set. A star cut set just means a vertex and its neighbors, so that if you delete them, the graph becomes disconnected. Right? And now suppose I found a star cut set in the graph, and this thing is connected. So I found a vertex with a connected neighborhood, and if I delete this vertex and its neighbors, the graph becomes disconnected. Well, that's again good for me. Why? Because in every 3 coloring, this part is colored, is colored in the same way. Right? That's what it means for this to be connected. Well, so now I'll take one component of the rest together with V and its neighbors and color that, and now take the remaining components with V and its neighbors and color that. And now I can claim you can put them together. And now I claim you can put them together. Why? Because this thing is colored the same in both. Because this thing can only be colored one way in every 3 coloring. So that's again good for you. And basically most of the arguments is you find a vertex, you prove its neighborhood is connected, and then you say, if I delete this vertex and its neighbors, that doesn't disconnect the graph. So for example, here, in this picture, so if you look at the vertex V, you can prove its neighborhood is connected, And now, so far in this picture, V and its neighbors disconnect U from the top part of the graph. Well, then there should be a path from U to the rest of the graph. You analyze what this path looks like, and you get that it must look like this. And that's one of the abstractions. You can see this is not trivial. And this is it. Thank you very much.
All right, thank you. Do you have any questions? Yeah.
Ibrahim Gary. I think you have another result related with planar graphs, saying that planar graph is precolorable if is wheel-free. I haven't seen any connection in this study, and since you assume, I think, that the graph is non-planar in arbitrary graph, would it be nice to have a connection with the precolorability of planar graphs with this result? This is my first question. My second question, is your precolorability result on planar graphs is the ultimate result for precoloring problem? Because I know Steinberg conjecture and many other conjectures, and the final result has not yet arrived. Thank you.
Thank you. The paper about wheel-free planar graphs actually talks a lot about the structure, and here we really only get an algorithm. So somehow, the situation there is much more restricted. It would be hard to. This recolorability there is, just a short corollary of a structure theorem, and here all we have is an algorithm. So that's going to be hard to bring together. And as far as whether that result is tight for planar graphs, I have no idea. We just noticed that we could say something about the structure of wheel-free planar graphs, and we did. We don't claim to, we don't mean to say there's something inherently special about those graphs.
All right, any other questions? Yeah, so now let's thank the speaker again.